A really neat activity you could do is called a ballistic pendulum. What I'm going to do is I'm going to shoot a golf ball at point blank range into this bucket, and the golf ball is going to be going crazy fast, but one of the calculations we're going to do is figure out how fast. There's actually going to be 10 different calculations we're going to be able to do with this, and this is actually going to be the final exam for my first semester physics class. It's one of 2 final exams. We'll have a multiple choice final as well. But here's the launcher, and I'm going to just shoot at point blank range. I'm using compressed air. The golf ball sitting right here, and it's going to fly into the bucket like this. It's hanging from the ceiling, and you see that box is there. Here we go. We're going to shoot and watch the box. See how the box just got pushed back there, and swing gently because I have enough mass on it to give it enough inertia so it doesn't go crazy. But here again we can see the whole thing in our view, but we got to take some measurements, and with those measurements we're going to do some calculations. But the first thing we're going to measure is just the initial position of the box, where the back of the box started from, and then after we shoot it the box moves to a final position, and if I know those two, of course we could subtract and find the distance the pendulum moved backwards. We do need to measure the length of the pendulum, the straight down vertical distance from the anchor point there straight down to the anchor point there, because we need to know how long it is so we can figure out how high it rose as it swung backwards. Another thing we're going to measure is just simply the mass of the pendulum. I'm going to put that on a bathroom scale and figure out how many pounds it is, and then convert that to kilograms. The golf ball, we want to find the mass of the golf ball, and I'm going to use an electronic scale to do that. The length of the barrel, we're going to measure how long the barrel is, because that's the force that is put on that golf ball through that distance. And then if I know the diameter of the barrel, we can calculate the pressure put onto it as well. Okay, but those are just simply the measurements we're going to take. Those are all the measurements we're going to take, and with those measurements, we do have to be careful to go in the MKS system, meaning all distances should be measured in meters, all mass should be measured in kilograms, all times should be measured in seconds. If we do that, all the other units are going to work out. Velocity, acceleration, force, pressure, momentum, energy, and power. We got to be careful to measure everything in the MKS system. And to borrow a line from The Martian, we're going to physics the out of this. Okay. Anyway, we've learned a lot over the semester. All of these are topics we've learned in physics, and it looks like a lot, but for this final exam, we only need to be really familiar with these 10 videos. And if you need to go back and look at those 10 videos, you are welcome to, but I'm going to cover how to do each one of the calculations. So the calculations we need to do. The first one is how high will the pendulum rise? As it swings back, it also rises up. How fast was the pendulum traveling after the collision? So ball collides and it moves backwards with some velocity. You noticed it wasn't going real fast, but we want to measure how fast. But I think what we really want to know is how fast that ball is traveling after it leaves our launcher, but before it collides into the pendulum. And then we're going to get an answer for that in meters per second, but maybe we should convert it into miles per hour so we can have a little bit more familiarity with it, or kilometers per hour. There's air pressure in this chamber, and then when I pull the trigger, it's going to put a force on that ball, and I'd like to figure out how much force in newtons was put on that golf ball. And I want to find how fast that ball is going to accelerate. We are going to be amazed at how fast that ball accelerates. The 7th thing is we want to calculate the average pressure in that chamber, because when I pull the trigger there and the air in here starts to expand and push that ball outward, the greater volume is going to have less pressure. So all we'll be able to do is measure an average pressure. But the 8th thing I want to calculate is how much time it takes the ball to go from there to there. And again, it's not going to be a lot of time. It's going to be an extremely short period of time. The ninth question is, if I shoot it straight up into the air, how long will it take to come back to the level that it was launched at? And the 10th question is, if I shoot that thing horizontally from some height, where is it going to land? And we'll use the velocity that we calculated of the ball up there. Those are the 10 questions. I'm telling you right now what the 10 questions are, exactly what's going to be on the final exam, one of the final exams, and make sure you know how to do those 10 things. So I'm going to cover each one of them specifically. But here's the general idea of the activity. We're going to shoot the ball. It's going to be going really fast, collide into the pendulum, and because the pendulum has so much more mass, it's going to be moving a lot slower than the ball was. But it's going to collide in an inelastic collision. The ball's going to stick to the pendulum and they're going to move off together. Either way, momentum is always conserved. The total momentum initially will equal the total momentum finally. And because there were two things, there was the momentum of the ball and the momentum of the pendulum before, and the same thing is going to be after, we have our equal sign there. One thing that simplifies things a lot is that the pendulum was initially stopped. Before the ball hit it, it had no momentum. So that's going to be our equation now. And then I can substitute in the things that calculate momentum. Well, it's just the momentum of the ball is the mass of the ball times the velocity of the ball. This thing had the ball combined with the pendulum, so the two masses add together, and the two things move off with one velocity. I'm calling it the velocity of the pendulum, but really it's the pendulum and ball combined. And I think we really want to know how fast was that ball traveling after it left the launcher, but before it collided into the pendulum. To do that, we need to know the mass of the ball. I'm going to use an electronic scale. We need to know the mass of the pendulum. I'm going to use a bathroom scale. And then we need to know the velocity of the pendulum right after it collided. So let's cover how we're going to do that. Conservation of energy is what we're going to do. Right here, before the ball hit it, this thing had no gravitational potential energy, but after it's going to swing, after it hits, it's going to swing back and rise up. Down here, it's at its lowest point, so no gravitational potential energy, but it has a lot of kinetic energy. Up here, it came to a stop at its highest point, so it had no kinetic energy, but it had all gravitational potential energy. So just this amount of kinetic was transformed into that amount of potential, and there's our equal sign. And once we recognize where our equal sign goes, then we can substitute in gravitational potential energy is mass times gravity times the change in height, or the change in the y-coordinate. And the change in kinetic energy is 1/2 mass times the velocity of the pendulum squared. The mass cancels out because it's on both sides. I'm trying to find out how fast it was traveling down here. So I'm going to multiply both sides by 2, and then I'm going to take the square root. So I can figure out how fast it's traveling down there. If I know what 2 is, it's the number 2. If I know what g is, it's 9.8 or 10, depending on what you want to use for gravity. And then we need to do a little bit of work to find how high the pendulum rose. But if I know those, I can calculate this. To figure out how high the pendulum rose, we're going to use geometry. And that's the first question, is how high did the pendulum rise? Well, we know the starting position of the box, we know the ending position of the box, and I want to figure out how high the pendulum rose up, because as it swung back, it also rose upwards. Now, if I subtract those two numbers, that's the horizontal distance, which is the same as the length of this leg of this triangle. And then the other thing I need to measure was the straight down distance from the ceiling to the pivot point. I need to know the length of the pendulum. So I'm going to call this side L. If I call this side L, what do you think we should call this side? Well, we're going to call that L as well because they're the same length. It's just the radius of that arc. But we have this triangle, and I bet you we could take L and D and come up with the change in height. And if we just measure what this side is, if we calculate what this side is, it's a right triangle, so we can use Pythagorean's theorem. This squared plus this squared equals that squared, or that squared minus this squared, and then square rooted is what this side of that triangle is here. And notice if I take the whole length here minus this length here, it would tell me this length here. So L minus the square root of L squared minus D squared is going to be how we're going to calculate how high the pendulum rose, our first question. But once we know that, we're going to plug that into our conservation of energy equation to figure out our second question: how fast was the pendulum traveling after the collision? Down here, that gave it velocity to move up to there. Once we know this, we can plug that in to our conservation of momentum equation. And I know the mass, I know the mass, I know the mass. We did a lot of work to find the velocity, but I know that now. That's our third question. And I can find out what this is, getting this by itself. It's being multiplied by the mass. So if I just divide both sides by the mass, that's how I'm going to figure out how fast the ball was traveling right after it was shot, but before it hit the pendulum. To convert that to meters per second, I got to convert meters into miles. I got to convert seconds into hours. And I'm using this number, but you'll use the number for the velocity that you calculate of the ball. We're going to start with 42.5 meters per second, and then I'm going to use unit conversions. I'm going to multiply by the number 1. And that is the number 1. Numerator, denominator are the same. 1 mile is the same thing as 1,609 meters, but because I have meters on top and meters on bottom, they cancel, and my unit would now be miles per second. Now I just got to get seconds into hours. I'm going to multiply by another fancy 1. 3,600 seconds is the same thing as 1 hour, so that's the number 1. But because seconds are in the denominator and numerator here, they cancel, and my unit now becomes miles per hour. So I just got to take this times that, divide by that, and I get 95.1 miles per hour. Okay. The fifth question is how much force in newtons was put on the golf ball. There's air pressure in here, but that pressure is going to put a force onto that golf ball. The thing that allows us to do that is the fact that 100 joules of work would cause a change in energy of 100 joules. The amount of work you do is the amount the energy will change. Or if I had 200 joules of energy, I could do 200 joules of work. So right here, the ball had 0 kinetic energy initially. Over here, it's going to have a bunch of kinetic energy. But if I just subtract those two, I could find the change in kinetic energy, or just 1/2 mass times the change in velocity squared. It had 0 velocity here, had a bunch of velocity, which we just calculated, but we can find out how much kinetic energy it got, and that's going to equal the force times the distance. Force times distance is work. So work is force parallel to the distance. If they're not parallel, you have to multiply by the cosine of the angle to find the component that is parallel. But this piece right here is called the work energy theorem, that this amount of work is going to equal this change in energy. And in this case, it was kinetic energy. So I know the distance, I know the velocity, I know the mass. I can just figure out how much force was put on that ball parallel to the distance. And then I want to find the sixth question is to find the acceleration in meters per second of the golf ball, meters per second squared, excuse me. And it's Newton's second law. It's just the relationship between force, mass, and acceleration. So we're going to calculate the acceleration. We knew the force. We just calculated it previously. We still know the mass of the ball, So we should easily be able to find the acceleration of the ball. The seventh question is, what was the chamber pressure? And it's going to be an average pressure. But pressure is force over area. Typically, we would measure the force in newtons and the area in square meters. So I could get the pressure in newtons per square meters, or the same thing as pascals. But I've got a pressure gauge on here that's marked in PSI. It's an imperial unit, pounds per square inch. So I would need to measure the force on here in pounds, and I need to know the cross-sectional area in square inches. Okay, so I can find the square inches if I know the diameter of this. It's 2 inches. And so the force divided by the area, it's a circle, pi times the radius, not the diameter, but the radius squared. So this is going to be in square inches. We had previously calculated this in newtons, but we got to get it into pounds so that we can get it into pounds per square inch. So we're going to take the amount of newtons that we previously calculated and multiply by a fancy 1. I hope you know by now that 1 kilogram of mass weighs about 9.8 newtons. So that is a fancy 1. Newtons on top, newtons on bottom cancel. And then I got to get it into pounds. I got it into kilograms. I'm hoping you know by now that there's 2.2 pounds is the same thing as a kilogram. So kilograms on top and bottom cancel. And I just take 2.2 divided by 9.8 multiplied by how many newtons we got, and that would be the number of pounds. Okay. The eighth question is how long the ball was in the launcher. And it's not going to be a lot of time. Okay. But it's very similar to the work energy theorem, but instead with momentum and impulse. We have to remember that an impulse is an action. It's something you do, and change in momentum is what results from that. So an impulse of 100 Newton seconds causes the momentum to change by 100 kilogram meters per second. So impulse equals change in momentum. So there is going to be a force put on that ball for some period of time. So force times time is impulse. And it had no momentum here. It had a bunch of momentum there. The change in momentum is just mass times the change in velocity. So there's our equation. Impulse equals change in momentum. I want to find the time. We had previously calculated the force. We had previously calculated the velocity. And we had measured the mass, but we can find the time. The ninth thing we need to calculate is how long the ball would be in the air if we shot it straight up. Now in my example, I'm shooting this straight up at 30 meters per second. And we know with the acceleration of gravity, when we shoot it up, it goes boom. But every second it loses 10 meters per second. And on the way down, it gains 10 meters per second every second. It accelerates at about 10 meters per second squared. So if we shot it up at 30 meters per second, it will come down with the same speed but opposite direction. And we can use our equation from linear motion. It's our first kinematic equation. But we want to find the time. We know the initial velocity. We know the final velocity. Here I'm saying the acceleration is -10. But on the exam, I will tell you if you should use 10 or if you should use 9.8, or if you should use something even more specific, like 9.79604 for the acceleration in Arvada, Colorado. Trying to get time by itself, if I subtract 30 from both sides, it cancels here. So I have -60 is equal to -10t. Still trying to get t by itself, it's being multiplied by -10. So if we divide by both sides by -10, -10 will cancel. I'm only left with t on this side, and -60 divided by -10. 6 seconds is how long it's going to take. The last and final thing we have to calculate is how far out will the ball land if we shot it from some vertical height, but we shot it horizontally, like this example here. So in my example, I'm using a train going 27 meters per second, and it fell 14 meters, but we would use the velocity of our ball and whatever height I give you at some later time. So anytime you do a projectile motion problem, you want to find the time that it takes to fall first. Because if I just hold that train and drop it and allow it to fall that distance, it's going to take the same amount of time as if it was just going straight horizontally and then landed out there. Okay? But there's our equation, and notice that the velocity is 0. Now, that velocity wasn't 0, but that was horizontal velocity. This was vertical velocity. Because we shot it perfectly horizontal, it wasn't aimed up with some vertical component or down with some vertical down component of velocity. It had no velocity up or down. And then I can just plug in the numbers. It was shot from an initial height of 14 meters. Gravity is negative 9.8. I want to find the time, but at that time is when it hits the water. 0 distance if we start there and measure up. If I solve for time, I find that it's 1.69 seconds. So that was the first step. I find the time first. Once I find the time, I can now find the horizontal distance out using the same equation. That's the same equation as this one. But this time, this is going to be 0 because we're going to start at 0 and measure out. And then this is 0. It was accelerating over here, but it's not accelerating horizontally. So there's no acceleration horizontally, and it is just velocity times time gives us distance at 45.6 meters. So those are the 10 questions. So these are all the measurements that I took when I shot that golf ball. And I just want to point out that I used measurements that were convenient for me, like the initial position of the box I measured in centimeters, but that's not an MKS unit. I should get centimeters converted into meters. And another one, like the mass of the golf ball. I put the golf ball on an electronic scale, and it gave me the mass in grams, which was convenient, but I would want to get it into kilograms. The mass of the pendulum was way too big to put on electronic balance, so I put it on a bathroom scale, and it gave me an answer in pounds, but again, you want to get that into kilograms. So just make sure each one of those answers there are in the right units when you do the actual calculations. So here again are the 10 questions. Please make sure you know how to do these 10 questions for the final exam. We are going to use 9.8 instead of 10 for the acceleration of gravity, but if you use all those measurements and this acceleration of gravity, these are the answers I came up with. And I put all of these in a spreadsheet, so these numbers are really exact. Are really, well, good to 3 sig figs at least. A couple things. Notice that if I convert into miles per hour, I had a golf ball going over 300 miles per hour in my classroom, and that's incredible. The acceleration of the golf ball was over 1,000 times the acceleration of gravity. This one, how long was the golf ball in the launcher? Just over 100th of a second. Or if I shot it straight up in the air, it's not going to come back to the ground until 30 seconds later. The last one, how far out will the ball land if I shoot it horizontally? I am giving you the height now that it was shot from the bridge 30 meters up. So you have to use 30 meters and the velocity to come up with that number there. Because I used a spreadsheet here, the spreadsheet kept all like 15 decimal places in every one of these numbers. So I've rounded these numbers. I'm not showing you all 15 decimal places. But if you do this on a calculator and you only keep, say, those 3 sig figs and you throw away the rest and then use that answer to calculate this one, well, that number might not be exactly the same as mine because your numbers you were using were just a little bit different. But if you got this number, which was a little different than mine, and you threw away a bunch of decimal places, well, then this answer is going to be a little bit further away. And you're going to get what's called propagation of error. As you go further and further and deeper into these calculations, your answers are going to get further and further and further away. So make sure you keep at least 4, maybe 5 significant figures in your calculations. But as long as you get something reasonably close, you can know that you're doing your calculation correctly. When it comes to the final exam, though, it would be terrible if you missed this first question and then therefore you got all those wrong. So I'm not going to do that. Each one you're going to take on its own, and I'll give you the information you need for each one of these on your own. But I'm pretty confident that you can do all 10 questions. If you have questions, you can ask me, but I wish you the best, and we'll see you on final exam day.